Section 6.7.3, we are going to look at similar right triangles and their altitudes to identify similar triangles that are formed and then use theorems of those altitudes in those right triangles and those similar right triangles to find missing values. Okay, so the similar right triangles theorem says if an altitude is drawn from the hypotenuse of the right triangle, so remember the altitude right here goes from a vertice and forms a 90-degree angle, is perpendicular with the other side. Okay, we're specifically drawing it to the hypotenuse. So in this large red triangle right here, this side right here is the hypotenuse. Okay, so this whole side, and we're looking at this triangle ABC. That is our large triangle, that large right triangle that we're talking about. And when we draw in that altitude, then it forms two other triangles that are similar to the original and similar to each other. So if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original and each other. So what that means is triangle ABC, the red triangle, is similar to triangle DBC, the blue triangle, and also similar to the green triangle, angle ADB. And keep in mind, these vertices and their orders are very important because AC is the hypotenuse in that red triangle. And in the blue triangle, it's BC. That's the hypotenuse. And in the green triangle, it is AC, which is the hypotenuse. And so if we look at the similarity statement, we can see that AC right here and BC right here and AB right here is the ones that are the hypotenuses. Those are the corresponding sides. And we also can take a look at the longer legs and the shorter legs, and we're going to write proportions of similar triangles to find those missing pieces. So sometimes when we do this, it's easier if we draw the three triangles separately. And from our similarity statement, I've highlighted which angles are congruent. So angle A in the red triangle is congruent to angle B in the blue triangle, and is congruent to angle A in the green triangle. Okay, those are all congruent because of the similarity statement. We can pick that out. And we also know, again, like I said before, that AC right here is the hypotenuse, and that will be the corresponding side to the hypotenuse in the blue and in the green triangle. And so we could actually fairly easy prove these two triangles. Like, let's just start with these two right here, the blue and the red, with angle, because we know that angle A, maybe I'll color code this with the colors. So in the red triangle, angle A is congruent in the blue triangle to angle B. And we also know the right angles are congruent. So in the red triangle, that would be angle B is congruent to the right angle in the blue triangle, which would be angle D. Okay, so we can prove those two triangles are congruent by angle similarity. Okay, so we could go through the same type of steps, okay, to prove the other two triangles, like the green and the blue, and the green and the red are also similar, but I'm not going to take the time to do that right now. Oftentimes, it's even easier for us to pick out the corresponding parts, not just with the similarity statement that we're given, but if we draw and turn all of the triangles so that they're orientated in the same direction. And so we can clearly see which are the hypotenuses, and we can also see which of these sides, okay, would be corresponding because they're shorter legs or longer legs. And those are the ideas we're going to use to set up similar triangle ratios and proportions to solve for missing pieces. So this first piece says to identify the similar triangles and then find the value of x. So here we have a right triangle. This is our large right triangle right here. And so triangle GEF is similar to the two triangles formed. We have the larger and we have the smaller right there. And so that will be similar to, now one thing you need to pay attention when you're writing these statements, I'm going to make that a little bit more looking like a triangle here. One thing to keep in mind is you can take that original similarity statement that you have right here and you can apply it and put in the new vertices so that you can just kind of go with it from there. Okay, but otherwise, if you're not doing that, you need to make sure you're putting the vertices in the correct order. So notice that in this case, GF is my hypotenuse right here. So I'm starting at G and I'm going to E, okay, along this side, which is the longer leg of that red triangle. And so I need to do the same thing when I'm writing the similarity statement for the blue triangle, is I need to start with the longer leg of the blue triangle and go towards the hypotenuse. So that would be similar to a triangle GHE. And then again, using that same strategy for the green triangle, I have to start with the longer leg of the green triangle. Right here is the longer leg. So then I would say that is similar to triangle EHF. And again, notice the hypotenuse GE and EF. Okay, those are all the hypotenuses. So first I identified all three similar triangles and make sure your vertices are in the correct order. Okay, and then to find the value of x, I'm going to set up a ratio of sides. So, x is what I'm trying to find. So I am trying to find x, which is this altitude right here. Well, that altitude happens to be the shorter leg of that blue triangle. So I know that the shorter leg of the blue triangle, so this is the longer leg of the blue triangle, this is the shorter leg, which happens to be x, compared to the shorter leg of the red triangle. So again, I'm trying to color code this. So the shorter leg of the red triangle, which is 3, that is going to be in the same ratio as we could do the hypotenuse, okay? So we know the hypotenuse of the blue triangle. Okay, this is the hypotenuse of the blue triangle right here, which would be 4. And then we do also know the hypotenuse of the red triangle, which is 5. So now we have a proportion. And so we can just cross multiply to solve. And we get 5x then equals 12, or x equals 12/5. And we can leave it like that or get a decimal if you prefer. Okay, so the key is to make sure you have the corresponding sides so that you can write a proportion to solve and find missing pieces. Here's an application. It's kind of worked out for you, but I'm going to try to kind of explain it anyway. It says that the diagram below shows a cross-section of a swimming pool. What is the maximum depth of the pool? So what you are trying to find is you are trying to find this depth right here. Okay? So that depth is h, we're going to have to find. But we need the whole depth, so after we find h, we are going to have to add that piece right there of 48. All right, so one thing to do is, again, identify the similar triangles. So here is the large right triangle right here, and they've redrawn this separately, which can make it easier. And then we have the other two triangles. Here is this blue one right here. And then we have this green one right here. Right there, okay? So we want to find the value of H, which happens to be TM. So TM right here is what we're trying to find. That is our H, okay? So we know that TM right there is the shorter leg of that blue triangle. So this is the shorter leg of the blue triangle. So we're going to set that up in proportion to the shorter leg of the red triangle, which happens to be ST. And then we can write another ratio with the hypotenuse of the blue triangle, which is TR, and compare that to the hypotenuse of the red triangle, which is RS. So now we fill in the values of those pieces, and we get this proportion to solve. So now when we cross multiply, we'll get our H value. H is approximately 59. But remember, that's only the depth that we found that we need to add in that 48. So our total length or depth of the pool will be 59 plus 48, or 107 feet. So again, just trying to keep all those things straight and use those similar triangles formed by the altitude. Okay, let's quickly review geometric mean. Okay, remember because the next two theorems have to do with the geometric mean. So the geometric mean of two numbers is the square root of the product of those numbers. And so when you multiply 8 times 17, you get 136. And in simplest radical form, I would look for a perfect square that goes in there. 4 goes in there 34 times, and then I take the square root of each separately to get to square root of 34. Okay? So that's how we do geometric mean. You can try some of these examples on your own, okay, to make sure that you can still do these questions. Sometimes you cannot simplify it anymore, okay, but go ahead and try the last one and then check the notes to see if you've done it right, okay? But remember, the geometric mean satisfies the proportion, so the geometric mean x is equal to the square root of AB, because it satisfies the proportion A over X equals X over B. And so keep that in mind, because these two theorems, you're going to see that you're going to have that common letter diagonally. Now, this next piece is trying to sort of explain the geometric means theorems in this right triangle with the altitude drawn to the hypotenuse. It says, in lesson 6.1, you learned that the geometric mean of two numbers a and b is the positive number x such that a over x equals x over b. So consider the triangle ABC from theorem 7.5. You know that the altitude CD forms two smaller triangles. Okay, so again, I've drawn in that altitude CD. And it forms the two triangles, like triangle 1 and triangle 2. We've sometimes highlighted them with blue and green. Okay? Well, when you, again, look at these, you have a longer and a shorter leg of each of those two smaller triangles. And so if we write a proportion of the sides of, like, the longer leg of the triangle 1 compared to the longer leg of triangle 2, that would be in the same ratio as the shorter leg of triangle 1 compared to the shorter leg of triangle 2. So now if I actually use the letters that correspond, I would get CD over AD is equal to BD over CD. And notice that these are the same. So that means is that CD is the geometric mean of BD and AD. Well, here's BD, that's the little piece of the hypotenuse, and AD, that's another little piece of that hypotenuse formed by the altitude. And you can read through this again to try to make sense and understand it, but what this is really showing you is that altitude, CD, is the geometric mean of the two pieces of the hypotenuse it splits. And that is our first theorem. It's the geometric mean altitude theorem. And again, it says in this right triangle, the altitude from the right triangle to the hypotenuse, remember the hypotenuse? That's the hypotenuse of that red triangle. So the length of that altitude, okay, in this case we're calling it Z, the length of the altitude is the geometric mean of the two segments. And we showed you in this last example why it works out because of the similar triangles, but it's a very fast shortcut for us to find a missing piece in the triangle at times. So Z, that altitude, is the geometric mean of the two segments of the hypotenuse. So we can see that Z is equal to then the square root of X times Y. So X is one piece and Y is the other. Now, that's the easier of the two theorems. The second theorem is the geometric mean leg theorem. So in a right triangle, the altitude, so again, I'm going to state this again. We have this right triangle and we have this altitude, okay? The length of each leg of the large right triangle, okay? So again, we have this large right triangle, okay? And the length of this leg right here, Y, okay, the length of each leg of the large right triangle is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So Y right here is the geometric mean of the hypotenuse, okay, that's the hypotenuse of the red triangle. What is the hypotenuse of the red triangle? Well, that is W plus X. And the segment of the hypotenuse adjacent to the leg. Here's the leg we're looking at. Which segment's adjacent to that leg? W. So that is your geometric mean leg theorem. So that piece is equal to the whole hypotenuse compared to just the piece of the hypotenuse that is next to the leg. So how does that work? Well, again, we can look at this with similar triangles. W plus X right here is the hypotenuse of the red triangle. Y is the hypotenuse of that green triangle. That is going to be in the same ratio of that red triangle. In the red triangle, the Y is the shorter leg compared to the shorter leg in the green triangle, which is W. And so we're still using that same idea of similar triangles and setting up corresponding ratios and forming true proportions. And that's why that Y value, that leg, is the geometric mean of the hypotenuse compared to the part of the hypotenuse that it's adjacent to. And the same is true for the other leg. So if we look at the other leg, Z, so Z right here is the geometric mean of the whole hypotenuse of that red triangle, which again, W plus X, and the portion of the hypotenuse that is adjacent to the leg, which is X. And again, using that similar triangle strategy, W plus X is the hypotenuse of the red triangle, and Z is the hypotenuse of the blue triangle. And those hypotenuses will be in the same ratio as Z in our red triangle is our longer leg compared to X is our longer leg in our blue triangle. All right, so let's try to use these to solve. And again, you don't have to use these shortcut theorems. Most of the time, you can just set up those proportions of hypotenuse to hypotenuse, short leg to short leg, etc. Okay? I'm going to use them for this particular problem, and I'll show you one piece where I will go back and use the actual ratios of the sides, corresponding sides. Okay, so find the value of X, Y, and Z. Well, first of all, notice that X right here is the altitude. Okay, so that altitude X right there is the geometric mean of the two pieces of the hypotenuse it splits. So this piece and this piece. So X is equal to the geometric mean of 7 and 3. So X is equal to the square root of 21. Okay? So that's using that first theorem, and that's a pretty easy one to use, okay? The leg ones get a little bit more complicated, but let's go ahead and try one. All right, so let's look at Y right here. So Y is part of that large red triangle that we normally highlight. It is the longer leg of it. So Y is the geometric mean of, so it's the square root of the hypotenuse of that large red triangle. So again, I'll kind of highlight this red triangle that we've been doing. So it's the geometric mean of the hypotenuse and the portion of the hypotenuse adjacent to the leg. So this would be 7. So Y is equal to the square root of 70. If we use, and again, we could use the same thing for the other leg now, Z. So Z right here, this leg, Z, is the geometric mean of the hypotenuse, 10, times the portion of the hypotenuse next to that leg, which would be 3. So we get Z is equal to the square root of 30. All right? So I'm going to go back just really quick to this Y. All right, so let's show you a different way to find Y right here. So let's say I want to find Y using a proportion. So Y right there is the hypotenuse of, I'll shade this one blue because that was what we usually did. So we have the hypotenuse of the blue triangle, which is Y, okay? And we can compare that to the hypotenuse of the red triangle, which is 10. And that will be in the same ratio as in that blue triangle. Now we need to find another piece that we know, which is the longer leg. So we have the longer leg in the blue, which is 7, compared to the longer leg in the red triangle, which is Y. And we have that will be in the same ratio. So now when we cross multiply, we get Y squared equals 70, 10 times 7. Then we take the square root and we get Y equals the square root of 70. So again, you can use, most of the time you can use either method, either using the shortcut sort of theorems or by using the ratio, using similar figures to set up a proportion. But that's the end of the video for 7.